Hello everyone, this is Shauna and I'm coming to you today with your check-in for Math 112. This week in your lessons you're going to be covering material on a new type of distribution called the normal distribution, or sometimes we call it the standard normal distribution. You'll learn more about that as you go through, but let me bring up the uh, the slides for you. You need to devote a little extra time to these sections because they do take a little longer than not the material itself, but going through the slides is quite a bit more. So just give yourself some time to take these in, and do make sure that you have all of the slides, because we got some reports that some people were having some difficulty with that. So let me share my screen at this time and show you the slides for 6.1, which is focused on the normal distribution, which, as I said, is a bell-shaped curve. At the beginning of the chapters, you're seeing this math common phrases slide, and in the math common phrases slide, you see greater than, the arrow pointing to the right, and you see all of the phrases that mean greater than. Similarly, for less than, the arrow pointing to the left, all the words that mean less than. So study this, keep this handy. This is going to come in very handy a little bit later when we start doing word problems and you have those phrases in there. This is your definition. Many continuous variables which have infinitely many values have distributions that are bell-shaped and are called approximately normally distributed. The theoretical curve called the normal distribution curve is used to study many variables that are not normally distributed but are approximately normal. This is things like normal growth curves in children. It could be the distribution of SAT scores. It could be even something like in healthcare, the distribution of like normal blood pressure or normal blood levels. When you get your blood levels from the labs and they tell you the normal ranges are based on studying tons of people, tons of individuals, that they then take the data and they create a statistical analysis of it and establish what healthy norms are. There are a ton of properties of the normal distribution. Before I continue, there are 31 slides in this presentation, so make sure that you have 31 slides. The properties, as I mentioned, you want to pay attention to. Let me show you that. The mean of the distribution determines the location of the center, and the standard deviation determines the height and the width of the graph. So when you have a large standard deviation, you have a short wide curve. When the standard deviation is small, the curve is narrow and tall, which is what she shows you here. If you look at the blue curve versus the red curve in the first picture at the top, the centers are the same, the heights are not. The red curve is higher and the red curve is a little bit narrower and taller, thus the standard deviation is different, but the means are the same. And in B, the means are different because the centers are different, but the standard deviations are equal. And in this case at the bottom, both pairs of means and both standard deviations are different. Now let's go over a few of these properties. There are more. She did fix this slide. It's not fixed on my screen, but she did fix this slide. The normal distribution is bell-shaped. The mean, the median, and the mode are all equal and located at the center. The normal distribution has a single mode. That means it has a single peak. The curve is symmetric about the mean. It's continuous, as we mentioned. It never touches the x-axis, and importantly, let me show you this on this slide right here. Whoops, not that slide, sorry. I want to show you this. The area under the normal distribution curve is 1. The total area underneath it is 1 or 100%, is what that last bullet said. And you're going to learn about something called the empirical rule. We studied this prior, but we're going to study this in more detail in this chapter. And if you recall, the empirical rule said that 68% of the data falls within 1 standard deviation of the mean. That means from 1 standard deviation less or below the mean to 1 standard deviation above the mean is 68%. We split 68 in half and we get 34 on either side of the mean. 95% within 2 standard deviations and 99.7 within 3 standard deviations. So this is your bell-shaped curve with its percentages, which we're going to learn to apply to problems in section 6.2. Now, sometimes we have what we call a normal distribution, and we have what we call the standard normal distribution. All the normal curves, anytime you see normal distribution, normal curve, think bell-shaped. That's what that means. When you see normal distribution, think of a bell. But if you see standard normal, that's a specific case of the normal distribution, such that the mean is 0 and the standard deviation is 1. And you'll have problems in your book that deal with the standard normal. You'll also have problems that deal with the normal. Don't assume that you have the standard normal unless it's stated so, or unless you see the z-score, which we're going to be getting into in the next section. This formula, you're not responsible to know. It's just she wanted you to see that the normal curves, whether they're standard normal or whether they're other normal curves, have equations that help define their behavior, and the normal curve is no different. So this is the equation of the standard normal curve. Later on in this section, you have the z-score right here. And you're going to be doing this, as I said, in the next section. But this is the way that you know you're dealing with the standard normal when you have z. If you have z equals 1.25, that's a standard score, okay? You'll be taking what we call raw scores and transferring them to standard normal scores. This will make a little more sense to you after section 6.2, but we're going to introduce how to find them in this section here. So the rest of this deals with how to use your calculator to find standard normal for standard scores, okay? You're going to be using your calculator. The rest of this focuses on that. All of the examples focus on that. And then there's 2 examples toward the end here. that focus on going the other way, finding z-scores when your areas are given. So when you want to find a z-score, you use normal CDF. When you want to find a, when you want to find a probability, I should have said, or an area, you use normal CDF. When you want to find a z-score, you use inverse norm. And these are explained to you more in the slides as they're given to you. The thing about inverse norm is you have the area from negative infinity, always from the extreme left, all the way to wherever your z-score line is. Not your zero, but your z-score line. So if your z-score line is very close to the left, you're going to have a small area. If your z-score line is far away, you're going to have a larger area, okay? Remember that since the entire area under the curve is 1, if you split the curve at 0 at the mode, then you have 50% of the area on either side of the curve. So actually for this picture, for example, they gave you the area between 0 and the z-score as 0.4066, but the area from negative infinity to the z-score line, the big white half plus the yellow is 9066. So this is going to be your answer here. And z-scores round to 2 places. Okay, so just to let you know that is 6.1. Now, let me stop sharing this briefly, and let me switch to 6.2, which is applications of the normal distribution. I'm waiting for the file to open. Let me share my screen at this time. Here we have 6.2, applications of the normal distribution. Now, this presentation has 26 slides, okay? So just know that the other one had 31, this has 26 slides. Let's see what this says. This is going to tell us about real world situations. We're going to use all of the mechanics that we learned in section 6.1 to answer real world questions, like what percentage of individuals are geniuses, or what percentage of a particular brand of light bulbs emits between 300 and 400 lumens, which both of those questions are going to come up as examples in your textbook and in your lectures. So she gives you a little recap here. Calculator instructions. Some of you have been asking. Here they are. The relationship between X and Z. Again, same formula as last section. More calculator instructions for finding areas under the curve. And then we have some examples. So notice here, it says most tests that measure one's intelligence quotient, IQ, are designed to have a mean of 100 and a standard deviation of 15. It is also known that IQs are normally distributed. In 1916, psychologist Louis M. Thurman set a guideline of 140 scaled to 136 in today's tests for potential genius. Let X be the measure of one's IQ. Sketch the distribution of X, and what is the probability that an individual is a potential genius? So the things that are bolded are the things that we need to pay attention to the most. The mean of 100 is the middle of the distribution. That's your mu. Sigma is 15. Normally distributed, you think bell curve automatically. Now, this emphasis on one IQ or an individual will become more obvious to you a little bit later when we start doing sets of data. So this is different if I say, what is the probability that an individual is a potential genius versus what is the probability that the mean IQ of a group of people is a certain number. And so that's why this is important. If we're dealing with pulling out a group of people, notice here we had some people, but we're dealing with one individual person. If we're pulling out a group of people, then the calculation changes just slightly, and it does change the answer. That's why that's highlighted right now. Okay, but there's several very good examples in here. IQ is one of them. There's some other examples that are given to you. I want to show you this also. This relates to doing the other piece of this. So it says referring to the IQ scores again with a mean of 100 and a standard deviation of 15. What is the IQ score for an individual so that he or she is at the 90th percentile? Remember, percentiles are people who are at or below where you are. So this person who's at the 90th percentile, they have a high IQ. 90% of people are at or below them. So there should be a lot of area on the left and a little bit of area on the right. So 90% to the left, 10% to the right. And when you put this in your calculator, you get inverse norm. And so we have to deal with the inverse norm of this function, okay? And you go from there, you find the z, and then you get the solution for this. There are several examples of this. This is very example heavy this week. They're fully worked out examples. So do yourself a favor, because a lot of the homework follows a lot of the examples, and try to do your best. And if there are some problems or we get some feedback, then I will be happy to make another video with some of the problems that people have found problematic. But until then, I wish you the very best. I hope that you're safe and healthy. I hope that you're doing well in your course. And I will speak to you, Lord willing, again very soon. That's all I have for now, folks. Talk to you later. Thank you very much.